The next charge distribution we're going to take a look at is the charged shell. So when we say shell in physics, we usually mean the surface of a sphere. So you can think about taking a lot of charge and spreading it over the surface of a baseball or the surface of the Earth. So since we're going along the surface of a sphere, the radius of our charge distribution is going to be constant. Today we'll just set that equal to 1. And the variables that are going to be changing for the charge's position are theta and phi, the two angular coordinates in spherical coordinates. You can think of these as latitude and longitude, respectively. And so we need to set up the points for these. So we're going to take, we're dividing up the steps. Theta is going to go from 0 to pi. Phi is going to go from 0 to 2 pi. You always need to have one going halfway around because otherwise you end up double counting the sphere. And since we're working in 2D, we're going to divide each of these by the square root of n. This is going to result in a little bit extra charge because we're dividing by we're dividing by the square root of an integer that doesn't necessarily have a nice clean square root. So it'll be, the total charge is going to be off by just a little bit, but it doesn't actually matter for our purposes for illustrating it. And we set up our loops here. We're looping over theta, we're looping over phi, and here we're creating each point charge. So the position is given as in spherical coordinates, where you have a mix of sine theta and cosine phi. Basically, everybody gets multiplied by r, so they're all the same distance out from the origin. And then the sine thetas and cosine phis and everything just determines where along the sphere they are in terms of latitude and longitude. Each of these will have a small radius compared with the whole sphere, and they'll each be colored red since we're dealing with a positive charge. And then here I've got the individual charge for each point charge. And I want to justify this formula to you later after we see the sphere in action. The rest of the code below here remains the same in terms of setting up our observation points and calculating the electric field. So let's hit Control 2 and see what we get. So here we've got our electric field vectors coming away from the shell. You notice that they are the same as you go around here. It's rotationally invariant. That's because the shell of charge, all the charge gets smeared across so that when you're outside the shell, the whole thing behaves like a point charge. So it has this nice spherical symmetry about it. And in fact, as you get farther away, these are going to decrease in size like 1 over r squared, just like you have with a point charge. Because when you're outside of a shell, you get to treat it like a point charge. And now I want to zoom in on this shell to show you why we had to set up that funny equation for the Q. If you look near the poles of this, let's call this one the North Pole, you see that the charges get closer together than they do out here at the equator. So at the equator, they're spaced out a little bit farther than they are at either of the two poles. And this was causing a problem for me earlier because that meant that there was more charge concentrated along the poles than there was along the equator, and that ruins the spherical symmetry of the problem. So what I had to do was change the charge distribution for each of these points based on how much area they're actually taking up. So this is not quite an accurate physical representation of the point charges. Basically, the area needs to get smaller the closer you get toward the equator, or excuse me, the closer you get to the poles, and the charge per point needs to get larger the closer you get to the equator, since they aren't taking up the same amount of space. And so that's what this equation does. What I've done here is I've taken the surface charge density, total charge divided by 4 pi r squared, and multiplied by the area of each of those little sections of latitude and longitude. So that would be r squared sine theta d theta d phi. Now there are no r squares on here because they've canceled out. So the only thing you have left is q total divided by 4 pi, and then times this. Think of this as like an angular area. This is a measure of what we call steradians, which is a square radian, sort of. So when somebody tells you that you need to do a 360 review of your company or your life or whatever, tell them, no, I'm going to do 4 pi steradians because we live in a three-dimensional world. So we multiply by sine theta, d theta, d phi. And you might recognize this. This is the thing that goes in the integral over a spherical distribution. If you've done, if you've had Calculus 3, you've probably seen this as an integral over the surface of a sphere. This is that little bit of area that goes in there, except it just doesn't have the r squared because it's canceled out with the charge per area that was over here. And it doesn't seem to make too big a difference for outside the shell. I was getting this same result, this nice spherical symmetry, because here any sort of errors associated with that are small compared to the actual size. So here our E magnitude is, or electric field magnitude is about 0.36. But where I was running into a problem was inside the shell, because when you go inside the shell, watch this. This is a cool visual, I think. You can go inside the shell here with your scroll wheel. Inside the shell, no matter where you are, you're supposed to get 0 electric field. And the reason for that is that even if you're over to one of the poles here, you're closer to these charges, but you have more charges over on this side. So we're supposed to be getting 0 anywhere inside the shell. And I wasn't getting 0. I was getting very much not 0, but it became obvious that it was getting stronger closer to the poles because there was too much charge of the poles. So this has fixed that problem. So let me demonstrate that for you. Let's move inside the sphere. So the sphere is radius 1. So we're going to go inside a radius of 0.01. So we are going to be 1/100th of a radius into the sphere. And so currently we're outside the sphere. There's no electric field. We're not measuring electric field outside. So we just have this funky looking basketball here. So if I zoom in, I get mostly 0 electric field, right? So these have mostly canceled out. In fact, you can see if there's a bunch of arrows superimposed, so they're all kind of pointing in the same stray direction. But if you take a look at the magnitude, we're looking at 0.08. So we're looking at a much, much smaller result. This is within the rounding error of the sum of the electric field. One way we can check this is by making this shell a little more shell-like by reducing the size of these point charges. So let's go back up to the top, and let's go from 1,000 pieces of charge along the shell to 10,000 pieces of charge along the shell. So here is our new shell. You notice it's taking a little bit longer to rotate around because it's taking up more memory. If I zoom in, again using the scroll wheel on my mouse, I still get a teeny tiny bit of electric field, but you can see it's gone down a bit. So it went from a 0.08 to a 0.07. So that's a good check for whether a real effect is actually happening. Is if you increase the number of points in your charge distribution, if this number decreases, then it's not really supposed to be there. It's kind of a fake number. It's left over from some of the rounding in the addition. Let's double check that claim by changing our ROBs back out to 5, because now we've got more point charges. We should get about the same of 0.36 that we had before when we were outside the sphere, and lo and behold we do. We still get a 0.36. So that tells me that that electric field inside the shell is not actually supposed to be happening, so that confirms, or at least supports, the claim that the electric field inside a shell of charge is 0. So we've had some fun with some charge distributions looking at the electric fields. Next time, we're going to take a look at creating contour plots to visualize the electric potential distribution of these charge distributions. So thank you so much for watching. I will see you next time. Bye-bye.